Hello students, welcome to my YouTube channel Rapid Chemistry, and here I am Ranjan. Today I would like to share you a very new unit, and that is rules for filling up of electrons in different orbits. Before we start this unit, I must say about whatever we have studied in the last day, that is orbit and orbitals. And you know what orbit? Orbit is based on the circular or elliptical path, and it is generally based on two-dimensional structure of atom. And orbitals are the region in space around the nucleus where the probability of finding an electron is maximum. Okay, and different kinds of orbitals are there, and we have studied that is the s orbitals. S orbitals are spherical in shape, and p orbitals, these are in dumbbell shaped. Okay, and two or more dumbbells can be combined to be d orbitals, and the d orbitals are these. Okay, and there are 5 d orbitals: dxy, dxz, dyz, dx square, y square, and dz square it should be. Okay, dz square. And for s orbital, only s orbital is symmetrical s orbital. It can be 1s, 2s, 3s, like this. Okay, and there are comparison in between 1s, 2s and 3s orbitals, and these are we have studied last day, and you must go through once again. Okay, and p orbital generally 3, so px, py and pz. Okay, now let's go through the electron accommodating capacity of K, L, M and N cell. Okay, so K is the very first cell, and from the Bohr's theory we know that in the K cell maximum number of electron can be 2, in the L cell 8, M cell 18 and N cell 32. And now with considering different orbitals, we will try to tally that fact. Okay, so let's look at here. On the very first cell K, that is the closest to nucleus, the principal quantum number n equals to 1. So azimuthal quantum number can be 0. L equals to 0. Okay, for L equals to 0, the M value can be what? M value must be 0. Okay, and then spin quantum number value can have plus up and minus up. Okay, plus up, minus up, and that represents subcell, and the subcell is 1s, and the number of electron that can be there on the very first cell, that is K cell, the 2. Okay, and the electronic configuration, and it is to be written like this: 1s2. That means in the first cell 1, s is subcell, and the number of electron that can reside there, and that is 2, and it is written 1s2. Okay, so hopefully you got that line. So K, n equals to 1, L equals to 0, M equals to 0, and spin quantum number will always be plus up and minus up. Okay, and the subcells is 1s, and that's how. Now let's look at here the second cell L, and for that n should be 2, and the possible quantum number, that is azimuthal quantum number, should be 0 and 1. Okay, for 0 magnetic quantum number will be 0, and the spin quantum number as usual plus up and minus up, and that represent 2s orbital, and the 2s orbital, s orbital, and at s orbital it can belong to 2. Oh, that is the second one, and that's why 2s. Okay, 1s means s orbital for first orbit, 2s means s orbital for second orbit. Okay, so and the electron that can reside there 2, and it is to be written like 2s2. Okay, and for L equals to 1, that is azimuthal quantum number L equals to 1, and definitely that represent p subcell, and if L equals to 1, the possible magnetic quantum number value should be -1, 0, +1, as it minus L to plus L. So, and the spin quantum number, these are, so the number of magnetic quantum number equals to number of orbitals. Okay, number of magnetic quantum numbers equals to number of orbitals, so that belong to 2p, and the 2p having 3 orbitals. Each orbital may have maximum 2 electrons, and that's why 2p orbital, and there is 6 electrons, and it is to be written like 2p6. Okay, and that's how these are done, and hopefully you can understand, and if not, definitely knock me. Okay. Okay, let's look at the this one for n equals to 4. N equals to 4. Try to go through that one very carefully. For the fourth cell from the nucleus, that is the n subcell, n cell, so magnetic quantum number value 4, and for magnetic quantum number 4, you know possible azimuthal quantum number will be 0, 1, 2, and there will also be 3. Okay, so for 0, the similarly you know m should be 0 and is spin quantum number plus up and minus up, and that represent 4s. Okay, 4s, and having the maximum number of electrons that can reside there, and it must be 2. Okay, s orbital always having 2 electron. And for L equals to 1, you know the 3 p orbitals are there, px, py, pz, and they all belong to fourth cell. Okay, that's why 4p, and the total number of electrons that can be 6. Okay, for L equals to 2, that is the azimuthal quantum number, you know possible magnetic quantum number values 5. So as I have just said, the possible magnetic quantum number value, that is the 5. Okay, so number of orbital will also be 5. Okay, so that represents 4d and 4d, and each orbital having 2 electrons, that's why 5 orbital will have 5 into 2, that is 10 electron. Okay, if L equals to 3, and you know that would be F subcell, and for L equals to 3, the possible magnetic quantum number values are these, minus L to plus L, and the total values are 7, and that's why 7 orbital will be there. Okay, and spin quantum number will always be same as that of plus up and minus up, as we have discussed earlier, and you know each orbital having 2 electron maximum, and that's why 7 orbital can and accommodate maximum 14 electron, and that's it. That's the capacity of F orbital. Okay, the correct ground state electronic configuration of an electron is obtained on the basis of following 3 principles. The first one, Pauli's exclusion principle, second one, Hund's rule, and the third one is above principle. So now we will study all these 3 rules in details step by step. Or the very first one is Pauli's exclusion principle. Okay, so in the year of 1925, after meticulous study of the line spectra of atom, Wolfgang Pauli proposed his exclusion principle, and it states that no 2 electrons in an atom will have the same values for all the 4 quantum numbers. Okay, so as we know, so each electron can be represented by 4 quantum numbers n, l, m, s. Okay, no 2 electrons can be found in an atom having all the 4 quantum numbers same. Maximum there can be 3 quantum numbers same, but not the 4th one. Okay, for example, I can say in the subcell 1s, okay, 1s, you know n value 1 1, l value 0 0, m value 0. Okay, and s can have plus up and minus up. That means in 1s 2 electrons can reside. So for both the electrons, the quantum numbers values are 1 0 0 half, and another electron 1 0 0 minus half. Okay, that means 2 electrons are there in 1s, and their 4 quantum numbers are set given, and 3 quantum numbers may be same, but the 4th one differs. Okay, with the help of Pauli's exclusion principle, the maximum number of electrons a subcell can accommodate can be calculated. For example, S subcell, you know the electron maximum can be there, that is 2 electrons. Okay, S, and you know for S subcell L value will always be 0. And if L equals to 0, therefore M should be 0. Okay, and you know the value of M will give you the number of orbitals, as I have said few minutes back. Okay, let's come to P subcell, you know L equals to 1, and then M should be minus 1 0 plus 1. Okay, that means for P subcell there can be 3 values for magnetic quantum number, and representing 3 orbitals. One is px, and one is py and pz. As we know, each orbital having 2 electrons, and that means 3p orbital will have 6 electrons. Okay, and let's go for D or subcell, and you know for d sub cell L equals to 2, and if L, that means azimuthal quantum number, then magnetic quantum number will be minus 2 to plus 2, that means 5 values will be there, and 5 values indicating the presence of 5 orbitals. Okay, and 5 orbitals means, and each orbital having 2 electrons, and that's why 5 orbital will have 5 into 2, 10 electrons. Okay, so for F sub cell, and the F sub cell, you know, for S sub cell, for F sub cell L equals to 3, and the M equals to minus 3, minus 2, minus 1, 0, 1 plus, that means 7 values can be there, and 7 value indicating 7 orbitals, and each orbital having 2 electrons, and that's why 7 into 2, 14, and that's how these are there. Okay, now let's look at the chart, and that is known to us already, the different cells K, L, M, N, and the principal quantum number value 1, 2, 3, 4. Okay, the number of electrons that can be there, number of orbitals. Okay, number of orbitals generally would be n square. Okay, for 1 square, 2 square, okay, 3 square, 4 square. That means for the third cell, total number of orbitals 9. And do you know how 9 came? That is 3s having 1, 3p having 3, and 3d having 5, total n. Okay, got it. So for this 2 1, the total number of orbitals 4, and you know how it came? So 2s 1 and 2p 3, that is total 4. Okay, so for the 4 principal quantum number 4, the total number of orbitals 4 square, that is 16. And how 16 came, you know, 4s, that is having 1, 4p having 3, 4d having 5, and 4f 7. So total number of orbitals become 16. Okay, and the electron accommodating capacity equals to 2n square, and that is already known to us from the last year, and that is 2, 8, 18, 32, and that is the maximum number of electrons that can be there in the different cells. In the last year we have studied how to write the electronic configuration, and there for say for oxygen, chlorine, calcium, and scandium, and electronic configuration is written like that: oxygen 826, chlorine 17 287, calcium 20 2882, and scandium 21 2892. And why it is so, and the explanation was not clear then, but now at class 11 we will learn all these in details. Okay, now let's look at the chart here given. So the, you know, for the very first cell only one S subcell is there, second cell 2s 2p, third cell 3s 3p 3d, fourth cell 4p 4p 4s 4p 4d 4f, and like that. Okay, and here these arrow signs shows that is the electron filling in the orbitals. Okay, and you know, order of increasing energies of various subcells, and generally electrons are filled at the subcell or orbital where the energy is minimum, and then it continues to enter into the orbitals where energy is more. Okay, and here so electron will enter at the very first in the 1s, then 2s, then 2p, then 3s, and it will go on like that. Okay, and for that we will know one rule, and that is n plus l rule. Okay, n plus l rule, and what is that one I will explain. We have to remember here above principle, and the above principle state that electrons are added progressively to the various orbitals in the order of their increasing energy, starting with the orbital with lowest energy. That means electron will enter at the orbital where energy is maximum at first, and then it progressively enter to the orbital where the energy is more, and we have to remember that order. Okay, so 1s 2s 2p 3s 3p. Okay, that means energy increases in that order from 1s to 2s. Okay, so energy is maximum for here 6d, and so on. Now try to understand the how electronic configuration is to be written. Say for oxygen 8 atomic number, you know, we were writing 2 6, but now we have to write that 2 electron in the K cell. That means, you know, in the K cell means first cell L s orbital having 2 electron. Okay, And for the second cell having 2s and 2p, okay, and the 2s having lower energy, and that's why it is to be filled first 2, and the rest 4 electrons are there in the 2p. Okay, so that's it is the electronic configuration for oxygen. Now you have to write 1s2, 2s2, 2p4. As we know, 1s having only one orbital, and that one having 2 electron, and those electrons having the different and orientation in their movement, and that's why it is to be shown like this, that, and 2s having also one orbital and having 2 electron, okay, and the 2p 2p having 3 orbital, 2px, 2py and pz. Okay, so that is representing 1s, that it is representing 2s, and that is 2px, 2py and 2pz. Okay, and now the rule says that at first we have to give one electron in each orbital. Okay, and these orbitals are degenerate means and then energetically same. Okay, all these 3 p orbitals of 2p are degenerate, that means energetically same. So at first they will fill L by one electron, and then there will be pairing. Okay, so that is the Hund's rule actually, and we will discuss right now. After oxygen, I am taking another example, say for chlorine, and how to write its electronic configuration. From the last year, we simply know the 2, 8, 7. That means in the K cell 2, L cell 8, and KL M cell 7. And now we will learn that is the 2 electrons are actually in the 1s subcell, and that is 1s2, and the 8 electrons are there in the 2s 2 electron and 2p 6 electron. Okay, and for M there are 3s, 3p and 3d, but 3s the having minimum energy, that's why it is to be filled first, 3s having 2 electron and 3s2, and the rest 5 electron are there in the 3p orbital. Okay, now how to show this? So the electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. You have to write, no dot, no comma or any sign is given in between these. Okay, so 1s means one orbital having 2 electrons, and their spin is different, and that's why it is to be shown like this. Okay, for 2s 2 electrons are there, and it is 1s and it is 2s. For 2p 3 orbitals are there, degenerate, and they are 2px, 2py and 2pz, and 6, that means they are all in the paired form. Okay, for 3s one orbital is there and having 2 electron, that is 3s. Okay, and in the 3p again 3 orbitals are there, they are degenerate, that is 3px, 3py and 3pz. Okay, and as we know, at first each orbital will have one electron at first, and then there will be pairing. Okay, so that's how the electronic configuration is to be written. Okay, now let's have some few simple examples for electronic configuration. Say for carbon 6, that means 1s2, 2s2 and 2p2. Okay, so nitrogen 7, 1s2, 2s2, 2p3. Oxygen 8, that is 1s2, 2s2, 2p4. And sodium 11, 1s2, 2s2, 2p6, and the last one here is 3s1. Okay, now from the very first element we will consider their electronic configuration. Say for hydrogen, atomic number 1, electronic configuration 1s1. That means the one that the first one representing is cell, and the s representing subcell, and the power 1, that means the number of electron. Okay, 1s1, and it is to be shown like that. Helium having 2 electron, 1s2, it is to be shown like that. Lithium 3, 1s2, 2s1, 1s2, 2 electron, 2s having 1 electron. Okay, beryllium 4, 1s2, 2s2, 1s2, 2s2. Okay, and next one, and boron 5, 1s2, 2s2. 2s and then it will be 2p1, but 2p having 3 orbital and they are degenerate as I have said, and any one orbital will be occupied with 1 electron. Okay, and after boron there is carbon and the 6 1s2 2s2 2p2, and it is to be written like 1s2 2s2 2p2, and those two electrons in the p orbital they must be in the unpaired form, they will not be in the paired form according to Hund's rule. Okay, and Hund's rule states that there will be the maximum electrons, and that means they are not in the form of pair. At first there will be at least 1 electron in each orbital. Okay, similarly you all try to go through all these. Okay, and and these are the noble gases. These are shaded because they are the exceptionally stable due to their electronic configuration. Neon having 8 electron, and that is the stable one. Okay, and after neon there is argon, and that is also very much stable in its electronic configuration. Okay, and but one or two exceptions are there in chromium and copper. Okay, and I will discuss these two right now. There are two important exceptions for the electronic configuration of chromium and copper. And chromium is 24 and the copper is 29th element in the periodic table. That means their atomic number 24 and 29 respectively. So electronic configurations of 1s, it will become 1s, first cell 1s2, second cell 2s 2p, third cell 3s 3p, and after 3s 3p, okay, 3d is not filling 4s. Okay, and why? Because the energy of 4s is less than 3d. Okay, and that is to be known from the above principle. And but here just try to observe d having 4 electron, and similarly for copper d having 9 electron. If there exists 4 or 9 electron in the d, okay, so it will have the tendency to take 1 electron from s, okay, and become very much stable. Okay, so for stability consideration these will remain same. Okay, and 4s, from 4s 1 electron will be given to 3d, and that's why. And 3d, d having 5 degenerate orbitals, and 5 degenerate orbitals will having 1 electron each, and that become very much stable, and that's why such tendency is observed. So you have to write the electronic configuration, not that line, you have to write for that line. Okay, similarly for copper, so d9 is there, but you should not write like this one, you should write the same up to that much. And for here 4s1 3d 10. Okay, it is because so whenever d orbital is half filled, that is d5, or full filled d10, and that is very much stable, and that's why we have to follow that electronic configuration. Okay, just remember that one, very important. At last I will discuss the electronic configuration of few anions and cations. Say for anions first, F negative. F negative means the number of electrons are there 10. Okay, so electronic configuration simply 1s2 2s2 2p6. Say for nitrogen 7th and element, atomic number 7, but it is in the form of nitride ion N3 minus, so total number of electron are there 10. So how to write? 1s2 2s2 2p6. That's how. Similarly O2 minus, that means those 2 electrons are need to be added there, so 8, it will be 1s2 2s2 2p6. Similarly for the other anions it will follow the same rule. But for cations sodium having general electronic configuration, that one 1s2 2s2 2p6 3s1, but whenever you are writing Na plus, that means 1 electron is lost, but that electron is to be lost from the last cell. Okay, last cell means here 3s, so for Na plus electronic configuration will become that one. Okay, say for chromium having electronic configuration, we have studied just right now that one. So if it exists in the 3+ ion, 3 electrons need to be removed, and that means 1 from the S1 and the 2 extra from D. That's why it will become D3. Hopefully you got it. Say for manganese Mn2+, so the electronic configuration is this one. Now the last 2 electrons need to be removed, but here that the 4s, those two electrons will be removed here and in the Mn2 plus ion, and the electronic configuration will be like that. So the very last one here is ferrous and ferric. Okay, for ferrous 2 electrons need to be removed. For ferrous, say for iron, electronic configuration is 4s 3d6 4s2. Okay, at first electron is filled at the 4s2 and then 3d. Okay, so but whenever the electron needs to be removed, and the electron from the outermost shell, it is to be removed. So that's why whenever the iron will form Fe2 plus ion, the electron will remove from the 4s subshell. Okay, 4s subshell. So Fe2 plus having that kind of electronic configuration, and Fe3 plus, that means one extra electron needs to be removed from here, and then the Fe3 plus will have d5. Now one question arises that which one is more stable, Fe2 plus or Fe3 plus? You have to know Fe3 plus is far more stable than Fe2 plus. It is because the d5, that is half filled d1 are there. As I have just said, half filled orbitals whenever having in an atom or ion, and that is very much stable. Okay, so thank you all for having concentration in this study. Okay, so study all this very nicely and knock me if you have any queries or any problem. Okay.